study of near-field binaural audio rendering in 6 degrees of field virtual platform.
Thanks, Ernst. So, good afternoon, everybody. My name is Olli Rummukainen, and I'm going to present a study we conducted some time ago in our lab on how to produce virtual sound sources close to the head in 6DoF virtual reality. I'll start with some background, why this might be a thing. So, first of all, about how do we reproduce virtual sound sources. We need something called the head-related transfer functions, or HRTFs, and I'm going to be referring to the HRTFs a lot during this talk, so this is what they mean. So basically they describe how the ears receive sound from a point in anywhere in three-dimensional space around the listener. And these are really individual, so they're affected by the physiology of the head and the shoulders and head size and everything that's close to the ears. And then we know that the HRTFs are different near the head, so near field would be considered about 1 meter away from the listener. And there we start to see some effects that are not present in the far field, so above 1 meter from the listener. So most notably, we get an interaural level difference, so ILD, so that the level between the ears is different at low frequencies. So this does not happen in the far field, it's only in the near field. Additionally, we get a small increase in the time that it takes for the sound to travel around the head, because it has to bend a bit on the way. So there's a small increase in that, but it's less significant. Now the thing is that we usually always measure the HRTFs only in the far field and then just assume that, okay, maybe they work in the near field, and maybe we can just use them as they are. So that would mean in this case that I have drawn here that the A and B are in the same azimuth and elevation, but the B is in the near field and the A source is in the far field. But if we only have the far field HRTFs, they would be reproduced. Both of these sources would be reproduced with the same HRTFs in that case. And what we then wanted to find out that is this really a thing? Should we really get the near field HRTFs and use them in VR, and what if we do it in 6DoF? So if the listener can move and the sound source can move and everything is kind of fuzzier, what does that do? Okay, so to approach this problem, we devised an experiment with 5 different ways to reproduce virtual audio objects in 6DoF. They were all binaurally rendered, except for one condition, that was a real loudspeaker. So first of all, the real sound source. We took a handheld loudspeaker. People can hold it in their hands if needed, and we strapped a 6DoF tracker on top of the loudspeaker, so we can bring it to the virtual world both visually and auditorily to the same exact spatial location. So that's the first one. Then we took the traditional approach, so let's only take far field measured HRTF, so measured at 1.5 meters from the listener. So that creates a kind of a sphere around the head where we can that we can use to reproduce sound sources. Then, to make it a bit more interesting, we obtained some multi-distance measured HRTFs. So these were measured from 0.5 meter up to 1.5 meters from the listener at 4 different levels. So this creates this kind of a layered sphere. So if we are closer to the head, then we can take the HRTFs from some closer layer of that sphere. Then this fourth condition is a bit different. So instead of measuring HRTFs, we can also model them from a spherical head model. So we can take a ideal sphere and compute from that what the HRTF would look like. And that was done here. And this was combined with extrapolating the near field effect. So we know physically how it almost approximately looks like, and we can create a filter that approximates this effect. So we combine this model with the modeled HRTF. So this is really a really fabricated case. Finally, the fifth condition, we took the far field HRTFs, so measured at 1.5 meters, but we removed the distance-based gain. So no matter how close you brought the sound source to your head, it was always equally loud. So that's quite unnatural, but then again, when you are in 6 VR, not everybody noticed that. Okay, so what was actually done? We took the 5 conditions and created this ranking by elimination task in VR. So on the upper right there, you can see the interface we had in VR. So all the 5 conditions are there side by side. People can listen to them, switch between them as many times as they like, and then eliminate them in the order of least preferred. So the one that's the worst, based on any criteria that people feel important, they would eliminate that and keep doing it until nothing is left in the panel. And this creates a ranking of the 5 conditions that we had. In the experiment, we had 2 different interaction types. So we had a static scene, and this refers to how the sound object was presented. So in a static case, the sound object would remain static. So we suspended the loudspeaker from the ceiling, shown on the lower left side there. And then the participant could move around it or below it or whatever made sense to them, but they couldn't directly touch the sound object or the loudspeaker in this case. The dynamic case, we gave the loudspeaker to the participants, and they were holding it in their hands and moving it around their head. And so 2 different interactions. Then we also had 2 different source signals. So we had a pink noise, so that's like supercritical signal that probably breaks all the renderers somehow, or it's easier to perceive any errors there. And then we had a cello, anechoic cello recording, which is more natural with some tonal structure and something that you might actually encounter in a VR environment. Okay, so that's the idea. Next, I'll show you a short video of how it looked like, and I'll walk you through it. So this is the static case. You can see that the loudspeaker is hanging there, and this participant is moving around it and trying to find differences between the 5 renderings. You can notice the headphones, so they were the AKG K1000, so they are open design. We can produce sound from the real loudspeaker or from the virtual renderings, and it should work with instantaneous switching there. So in this case, he eliminated the C first, and then he would try to find the second worst, and so on. And then the dynamic case, so same task, but now he's actually moving the loudspeaker himself there. Important thing to notice here is that we didn't guide people what to actually do there. It was really up to them what kind of movements made sense to them, what they wanted to do. So if somebody didn't, for example, test the distance gain at all, then they wouldn't perceive it. So it may be a factor in our results. Okay, so that's the idea of our experiment, and then I'll go through our results. So we had a pile of ranking vectors, and then we considered them as a series of paired comparisons and fitted a Bradley-Terry statistical model to it, so we can get preference weights for each of the conditions. So that would describe how likely any of these conditions is to win in a paired comparison against any other condition. And a nice feature of the model is that we get a ratio scale out of it. So for example, between the 2 best ranked renderers here, there's a 1.15 times higher chance that this one would win against the second best. And similarly, compared to the worst one, there's 2.23 times higher chance for the best one to be winning if they were compared pairwise. Yeah, and of course, if you're higher in the scale, you are more likely to win in a paired comparison. Next, I'm not going to go through everything. I'll just point out some key factors here. So first of all, we can say that the multi-distance measured HRTFs and only far-field measured HRTFs were consistently the most preferred in all of the scenes. So yeah, actually the 4 different scenes are here. So first the static scenes with cello and noise, and then the dynamic scenes with the cello and noise. So that's why we have 4 panels. And then small difference was found with the cello sample. So there the multi-distance measured HRTFs actually slightly won on the only far field compared to the far field condition. Then, interestingly, the real sound source didn't do that well in the static scenes. It did better in the dynamic scenes. It was comparable to the binaural renderings with this dynamic interaction, which is interesting. And then the distance invariant gain was more noticeable with the dynamic condition. So yeah, well, obviously it was doing pretty badly anyways, but even worse with the dynamic case. Okay, a few words, because we were also a bit puzzled by our results, so some reasons why we obtained these results. So we were expecting to see more benefit of the multi-distance measured HRTFs, but the thing is that we only had measurements down to 0.5 meter from the listener. So actually, the really interesting effects happen within 0.5 meter, so we would need to obtain better HRTFs to really make a meaningful comparison there. Then we assumed that the modeled near field would perform better because it's almost the worst one here. But this is probably more due to the rendering method, because we derived the HRTFs from the spherical head model instead of measured HRTFs, and that was more significant effect. So we cannot really say that this is because of the modeled near field. And finally, the real sound source did pretty badly. So we didn't match the acoustics to the actual, or the acoustics in the virtual cases to the real room. So there was a big mismatch there, and people were probably confused at what is going on here, and that should be better taken care of in the future. Okay, then to summarize, we found only a small difference between the multi-distance and far-field HRTF sets. So based on our results, multiplying the workload with measuring multi-distance HRTFs maybe is not worth it, but we would have to do more research on that to be really sure. Similarly, it's still really too early to draw any conclusions on the modeled near-field effect, so we would have to have similar underlying rendering method there to actually say something. What we can say is that the interaction method really mattered. So if people were able to dynamically move the sound source themselves, they gave different ratings, and they actually also completed the task faster than with the static setting. And all in all, this should be seen as groundwork for future experiments in this field. We are going to continue working on the topic, and hopefully someone else is inspired to do the same. So thank you very much. I'm happy to take any questions.
Bernd Fröhlich from Weimar University. Really great work. It's very surprising that the differences are so little. But did you look at the functions? Did you analyze the function? Because you've got functions, right? The near field and the far field function, or the multi-distance and the far field function. And you could compute the differences between those functions.
Yes.
And then you could maybe see if there are substantial difference or if they are quite similar. If they're quite similar, you know, you wouldn't even have to do the user study maybe.
Yeah, exactly. Good point. We have the comparison in the paper. You can look at the plots there. So we obviously did objective evaluation as well.
Yeah, I haven't looked at it, and you didn't show it. So, but
yeah, I'm sorry, I didn't.
Can you say something about the differences? Do they seem substantial, or they are hardly noticeable?
Yeah, they are substantial. So with the multi-distance measure, there are obviously these 4 zones away from the listener. It's constant within the zone, but at least you get the zones there. The level difference, for example, is about 20 dB at low frequencies close to the head. So that's a big effect, I would say. But all in all, listening to it, it's not very large. So.
Any further questions? I have one actually. I'm just wondering if you could have a practical example where let's say, the performance of the matter really makes a difference in VR. Sorry,
I can also.
Yeah, okay, sure.
So, is there any practical case where the near field effect really matters in VR? Yeah, I think it really comes down to the stimulus, the sound signal that we are trying to reproduce. So maybe it was also a case here that these sounds that we used were not something that you would really consider having close to your head. So For example, from some previous discussions, maybe if you have some like buzzing, like bee sound that's plausible to have near your head, then maybe it's a more significant effect than.
Let's thank the speaker again.